All right. Everybody hear me? Great. Well, welcome to Paint by Numbers High Performance Drawing and WASM. My name is Sean Isom. I'm the CEO and founder of a company called Renderlit. And today we're here to talk about Wander, which is a cross-platform rendering framework for WebAssembly. More generally, how do you draw data using WebAssembly? Let's dive right in. Is my mic not working? Is that better? I will talk louder. How about that? So drawing in WebAssembly, what do we mean by this? A lot of people might think this is kind of a solved problem. So obviously, WebAssembly kind of had its roots in a browser, and so there's applications that draw things in a browser in production. And this has been one of the more successful applications of WebAssembly over time. And some examples of that are Adobe Photoshop, AutoCAD has a web version. Google Maps, I think, is like the quintessential use case for taking a C++ code base, putting it in a browser, doing rendering via WebGL. I think the fact that gets hidden from a lot of these success stories of WebAssembly is the web is a very different platform from native applications. So although all of these are success stories, what you don't see are the war stories along the way. And yes, I love the power, I worked at Adobe before this, I love the power of things like Photoshop on a web browser because it means without downloading software to my computer, I can deface the Mona Lisa without ending up in jail. And this is kind of my central point behind this talk and behind what I'm building. Cross-platform is not really cross-platform in the way that we like to think it is. And that's the thing. All of those apps were like 10-year journeys to get these native code bases to work in a web browser. And you have technologies like Canvas, web browsers, if you're not familiar with how they work, accelerate things like Canvas and SVG APIs by transferring that on the GPU process back to a GPU and rasterizing it. You've got technologies like WebGL, which is how most of those apps I just mentioned were written. WebGL is a very old graphics API. It does the job, but it is another platform. WebGPU, likewise, a much more modern graphics API. It's like a 2014 maybe snapshot of GPU APIs, but it is another platform. All of these are tooled on top of JavaScript. So if you're a native app developer, and there's tools within Rust, there's tools within C++ like Emscripten to basically access these browser-side APIs, but you have to go over these JavaScript shims to access it. And so, when you're writing C++ code and you think you're accessing a GPU, you kind of have to change your mental model a little bit to say, well, I'm writing WebGL code, which looks a little different from my graphics code on different platforms. I'm going over these automatically generated JavaScript bindings. It works. I want to be clear, it works. It doesn't work super well. So, raw WebAssembly now. So we talked about WebAssembly in a browser, but what about actual drawing in WebAssembly? And the short answer is, you can't. That's it. you can't do it. And I mean, that's because WebAssembly in itself, you get I32, I64, F32, F64, right? Those are the basic types exposed by WebAssembly. And so other people have tried, different approaches to solving this problem before. There are like framebuffer style APIs that expose, essentially a rendering target, a pixel buffer to WebAssembly guest modules. There are some successful, I'm drawing a blank on the main one, I think it was from wasm. There are some approaches that have been taken to expose this through I/O devices to apps. Problem is, that does not use a GPU. That means you are compositing client side on the CPU into a buffer. And so that's not very high performance. ML, you just saw Radu and everyone up here talking about accelerated machine learning. Likewise, that is copying model data into a host API. So it's not exactly exposing like bespoke functions to do things with GPUs explicitly to WebAssembly guests. But that kind of gets us on the path of things like WASI and the component model and everything else that you've heard about at this conference, hopefully over the last 2 days. And so an idea is okay, given kind of this progression towards the component model and towards giving WebAssembly more features, can we add rendering capabilities? The answer is yes, we can, but it is a long journey to get there. So I want to talk about Wander. Wander, which stands for WebAssembly Renderer, very advanced name there, was my attempt to build a library that was a cross-platform rendering engine based off of WebAssembly. It's there on GitHub, scan the QR code, start the repo. I would appreciate it. So the idea behind Wonder is you take the entire graphics pipeline, you compile it to WebAssembly modules. You take your graphics code, you take your graphics data, you take everything, and you compile it down to a single file that effectively, or a stream of files that effectively can be embedded inside any application and run by a WASM runtime. And so you can kind of think of this as like in a browser, you're going over this JavaScript shim and you're talking to these browser-side host APIs. Outside of a browser, this gives you the ability to take those graphics, run them on GPU. So it's a cross-platform runtime. Basically, it provides a host-level layer that talks to the underlying platform's GPU API. Right now, it supports OpenGL, DirectX, and kind of WebGPU as of last night, conference-driven development. But the basic idea is you've got this host interface that exposes the GPU to WASM. And before I go too deep down more of the actual WASM path, let's talk about designing a renderer, because this might be a kind of opaque topic to lots of folks. Working from first principles, there's no shortage of libraries that exist to put pixels on a screen today. So we do not want to reinvent the wheel. We do not want to reinvent graphics programming paradigms. We want to expose things to developers in terms and ways that they are familiar with. So this means we are not going to re-implement WebGPU, for example. We're not going to build tons of different APIs that do all these different things. It's a huge API footprint. A renderer must be extremely high performance. This is most obvious when you're doing 3D games, for example, something where you need 60 FPS, something where you're rendering massive amounts of data in parallel. And so if you think about how a lot of WebAssembly systems design, they're designed to be pretty, say, CPU heavy, right? You've got a core that's doing a thing, or it's designed to be kind of broad. Let's say you've got request handlers, you're running the serverless platform, and you're responding to 20,000 requests per second. Renderers are kind of unique in that they share characteristics of both. You need extremely high single core performance for main loops, but you also need to be able to render these massive amounts of things like large pixel buffers to be able to take advantage of the parallelism of GPUs. And so the approach we took was to kind of be incremental with WASM. And that's I do not necessarily want to expose every single function to the WASM guest. We want to be able to talk to a platform's GPU API on the host side, not poke a bunch of holes in the security sandbox, basically take WASM linear memory, copy data out of it, and talk to the host via a wire format. And this allows it to be fairly decoupled. Okay, so now we get to the fun technical details of how all this is implemented. So first is kind of the node and the DOM tree. So over there is an example of what a node's sandbox would be like. So you can think of the sandbox as it's a WebAssembly sandbox, right? So it's it's actually a WASM module. And so within that, you've got nodes, which is the gray box, which corresponds one-to-one with an object that ultimately gets uploaded to the GPU. Inside that, you have steps. So you see there's a series of libraries over there that do rendering. We've got libraries for 2D, 3D, procedural content generation, and color operations right now. I'm working towards an open source model for contributing libraries to this. So right now, that is not part of the core runtime, but we want to get there. But the idea is these functions are exposed to guest code in WebAssembly. The guest code uses them. It puts data in memory. And then the host copies that data out of memory onto the hardware. There's kind of some design trade-offs I don't want to get too deep with between what is a node and what is a step. Because when you're running a DOM, like a node tree, a render tree, you can basically have every individual step within that tree be backed by a GPU object. Or you can run all of that CPU side and actually end up with just the end result being backed by GPU memory. With this, we decided to take the former approach, and that's because if you have to copy data out of WASM linear memory to the GPU, every single step, every single geometry operation, every single fill for pixels, that's very expensive because it basically it causes you to interrupt the entire rendering pipeline just to copy these small bits of data. So we don't do that. Okay, so that is the overall model, the memory model. And this has actually been probably the hardest thing about building this right now, is there does not exist there's not a high performance way to copy large chunks of WebAssembly memory across and share them across multiple guests, or copy them from host to guest, guest to host boundaries. When you have a throughput that's measured in gigabytes of data per second, this is actually a really hard problem to solve. And like, nothing against the component model or anything, but this is kind of more of a core memory problem of how do we give these multiple guests access to memory that is then backed by GPU buffers, ultimately on the host side, but do it without having to do a million mem copies and a million interrupts along the way. So given that background, there's a few different approaches to this. So individual buffers per node in a render tree. That's kind of the naive approach. Too many mem copies. You can iterate the render tree, and you can create a GPU buffer using the host API, and you can upload in real time, and then basically you just see your pipeline throughput slowing down. A better approach, which is the current approach, is pooled host buffers. So with this, there's a single GPU buffer that is managed by the host runtime per WASM module. And with this, all these different things that run inside it ultimately end up in slots in that buffer, but we wait for the execution of the entire render tree to copy the data once out of all. So sorry, let me take a step back. We copy the data out of each WASM node as it completes, but then we upload to the GPU once, because that single upload to the GPU is much more efficient than a bunch of small calls to the GPU. Long story short, if WASM multi-memory actually becomes a thing, that will solve a lot of problems here. I think we're a ways off from that. Last time I checked, although technically the proposal is level 3 or graduating to level 4, guest language support is very, very spotty for this because it requires an LLVM patch. So, but if we can get to a model where I can effectively build a single memory that thousands of nodes within a render tree can share and slot into and render in real time and parallel their data into, then there's not all these different mem copies. I run the execution of the tree, upload to the GPU once, it's extremely efficient. And that gets us to performance. See over here on the right, we might need to wait for that GIF to reload here. This is a performance test I did in a Maps app. Can I get this to reload? Yeah, there we go, okay. So watch, it's going fast, filling all these 3D buildings, and it kind of slows to a crawl. And why does it randomly slow to a crawl at a certain place? And that comes down to how we manage these core WASM time constructs. And I don't know, maybe I just don't know, but in writing code against the raw WASM time C API, there's not a lot of documentation or tribal knowledge out there on things like how do you size your store? How do you size the memories of these individual WASM modules? And how do you predict and how do you shard all of these things? I found that and yeah, by the way, this is all using WASM time, if that wasn't apparent, which is a great runtime, but the linker from it is pretty slow. So if every single one of those buildings there represents a WebAssembly function, and I am relinking all of those every single time that is called, the throughput slows to a crawl. And so ultimately, we group like objects and have to reuse their WebAssembly stacks. And that's fine because they're still sandboxed, they're still safe. It's a known set of inputs and known set of outputs. But effectively, we do not want to re-invoke the linker every time we need to reuse a function. Okay, last bit, hopefully, of technical material. Parallelism. So when we talk about parallel rendering, there is both data level and task level parallelism. So when we talk about data level parallelism, if you think of, like, what is a massively parallel operation? Like a lot of machine learning stuff. You're running large amounts of matrix operations effectively on these giant size vectors. The problem when you implement the CPU side is you can build these task graphs that are incredibly complex. And you can say, okay, like I'm going to schedule this graph where if I have an operation that does, I don't know, like, what's a good example of this? Like rasterization, for example, right? Like I know I need 1,000 rasterization ops per second. I know I need to render vectors. I know I need to be able to transform, like do a matrix multiplication. You can build thread pools for each of these operations. That's really painful. Like it's not a general purpose solution. So my take on data level parallelism is this is best left to the shader code. Like if you're doing like large vector size processing. So within this, we implement task level parallelism, which is where we say, we're drawing a certain number of objects onto the screen. We're going to split our scene up by effectively how many CPU cores we have access to. And so we are going to create a linker, a store, all of these different constructs per core. And then basically we're just going to divide the scene up and render them all through that. And so that way we can effectively use all the CPUs. You don't have to build all this fine-grained parallelism. I mean, there is an overhead to, instead of doing, like 1,000 of the same thing in a row, to hopping from one thing to something else, to something else, to something else. But ultimately, this gets us the best throughput. So this takes me to the V1 architecture. I apologize. This is a complicated slide. But overall, where Wonder is right now is the Wonder SDK can effectively create this node sandbox, create these WebAssembly modules, run these modules of graphics code, generate data, and upload them to the GPU. If you're familiar with how graphics are rendered, there's kind of two parts to the overall graphics pipeline. There is content upload, which is usually a multi-threaded process, and then there is the actual rendering of the data. There's the draw call. There's attaching a shader and telling the GPU to put it into a buffer. And so right now, we just handle the former. We just handle the upload to the GPU because it gets very tricky once you try to figure out, like, oh, if we go back to those first principles, I do not want to build a new shader system and a new shader generation API. We do not want to reinvent the wheel there. So here's some paths we took there. The naive path is, we talked about this before, exposing the frame buffer to raw WASM code. That's not actually GPU accelerated. There's an interesting approach, this Git repo here, not my code that I tried, that allows you to basically take WebAssembly code and through SpearV, compile it to a shader. It's kind of quirky because, like, if you've ever written code for massively parallel processors, it doesn't look a whole lot like code that you run on the CPU side. So like it's a subset of both sets of instructions because there's a lot of quirks. It's an interesting idea. So the real answer is the wasm-bindgen needs to be able to programmatically build shaders. And let's take a slight detour to talk about like what you need to do to invoke shaders. You have to be able to compile them. And actually here, graphical example here. If I click this link, is this going to, it opens on this screen. Hold up, can I? Does that, oh, right side. There we go, cool. Okay, so this is Shader Toy, if anybody's seen this before. This is credit to Fabrice, who puts together a bunch of these awesome shader demos. So like this is a shader. You've got code. This has to be dynamically compiled, and you don't just compile it once. You compile it to a specific format for a graphics API. But the problem is, it's not just the shader. You see, there's inputs and outputs to those shaders, right? And that's where you have to look at the entire graphics pipeline. You've got uniforms that are getting passed in. You've got attachment to these different buffers. You've got a scene state that defines camera position. You've got all these different building blocks that come together to give you an actual graphics pipeline. And so, like, going down the path of just dynamically compiling shaders is interesting, but there's a lot more. Here, let me kill this now. Cool, we're back. There's a lot more other things that are necessary to actually get that pipeline state to say, if I've got a raw canvas and I've got data I've uploaded to the GPU, how do I actually take it from GPU buffer to pixels on the screen? Sorry, I lost my mouse. There we go, we're back. Okay, so how do we solve this? Architecture v2. This is where Wonder is headed. This is probably going to be a one-year journey. Follow these beautiful magenta lines here. The idea is host app gives Wonder configuration on what is my scene state? Like, what does my frame buffer look like? Like, what does my depth buffer look like? Do I have weird output formats like motion vectors if you're doing TXAA, for example? Give me a declarative specification for what the render target looks like and all of the things I need to know to be able to draw into this arbitrary render target. Give me into WebAssembly functions to draw into that render target. And the beauty of this means now the GPU is exposed to WebAssembly, and WebAssembly can actually render anything as a guest module onto any canvas. Just let the gears start turning about how powerful that might be. But I didn't actually say how we expose the GPU. So here's a couple different approaches. For example, some people have tried to do this before. Friends at Azobo Studio who build Microsoft Flight Simulator have like interesting API here for doing 2D graphics, where effectively you can pass things in from wasm-guest to wasm-host that are copied into their engine, and then is composited into their overall rendering pipeline. I started going down this path. I realized very quickly that like this is a lot easier for 2D than it is for 3D, for one. And secondly, again, back to first principles, I do not want to wrap every single function from a graphics API. Likewise, look at it just exposing a platform's graphics API. Can we wrap that and expose that to WASM? It's at least a much more complete feature set. Like for example, let's take OpenGL and rewrite it where every single function is linked in WASM time to be exported as a WASM guest function. Not a great idea either. Oh, and then Flutter. Sorry, I missed that one. So link down there. Flutter is doing some. I don't know if Kevin's in here. Flutter is doing some very interesting stuff with Impeller and their GPU framework, which is not just WASM based. It's a general GPU framework, but it's the same kind of idea where you're building these abstractions over the raw underlying platform in order to give the guest a higher level API that still gives them raw GPU access, but in a safe cross-platform way. So the problem with building these layers yourself is you have to do some really hard things like bounds checking manually. And like, okay, everybody's written if statements say like if less than 1 or greater than whatever, blah, 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 right? But getting that right and getting that right across such a massive API footprint and not having security vulnerabilities is actually a challenging problem, as is resource ownership validation. So if anybody in here has done web dev, you're probably familiar with cores. And so likewise in a browser, the way we keep things safe is from content process to GPU process, ensuring that only resources, which is like basically effectively things that are backed by VRAM, can be accessed by the origin that owns that data, and not let anybody just basically write arbitrary data into VRAM and take over anything else. And this is an important concept because like a lot of people think like, oh, security for graphics, maybe that doesn't matter. You're just putting pixels on a screen. But realistically, VRAM is just like RAM. You can be running very intense calculations on that, and there's potentially data that can be extracted from that is a security problem. So, what is the solution to this? WASI WebGPU. Mindy, sitting back there in the back, put together this awesome library that is now the foundation of a level 1 WASI proposal that is WASI WebGPU. And the idea behind this was to take WebIDL, convert it to WIT, expose it to the component model, and then basically on the back end, it effectively could run any WebGPU backend, but with this, it's through WGPU. And so mapping that front end specification, which is the component model, WIT generated code, to WGPU functions on the back end. This is already a part of Firefox's rendering engine, and like this solves a lot of those problems we just talked about with running arbitrary content and security. So WASI WebGPU is the ultimate solution to this. And that kind of takes me to like, is that solve everything? Does WASI WebGPU negate the benefits of Wonder? And I don't think so, because WASI WebGPU, all that V2 stuff is going to be tooled on top of it, hopefully within the next year. Wonder will be a higher level API that effectively lets you write functions that compile down to WebGPU functions that can then be embedded inside any device. But the WebGPU is the how, not the why. And the why, I think you should be able to do drawing in a WebAssembly app that is not hosted in a browser, is you should be able to write user interfaces or write 3D graphics or anything that can run anywhere independent of the platform. It should not just be limited to the web. You should be able to embed this code inside any device. Like your UI doesn't necessarily have to be completely attached to the state of the application. And if we can keep these APIs higher level, we can effectively like let people be graphics programmers without being a web GPU expert yourself. Well, I don't know why that went so fast. Okay, live demo time. I got this demo working last night, so let's go and hope it still is. Okay, so first things first. So I have Wonder here as an OpenGL-based Mac application. So the code for this is all on GitHub. You'll see the link at the end. But basically, we have embedded a WebAssembly module using Wonder to draw arbitrary data using OpenGL. Yeah, cool. OK, so not very exciting demo, but basically like the quintessential hello world OpenGL demo there is the spinning red box. And we've taken this model of a 3D building that was generated programmatically using Wonder and embedded it into that same canvas. So that's cool. Okay, now the real fun starts. Now I have a Windows app. I'm running in a VM, DirectX 11 based. And if my computer does not call it quits here, I don't know what's going on with that. Well, wouldn't be a demo without Windows deciding to do something weird, huh? Oh, okay. Something happened. I don't know if it's something good, but... Oh, hold up. Is it rendering off? Oh, there it is. Okay, it's because it's full screen. There we go. Cool. So this is that exact same WASM module embedded inside a DirectX 11 application on Windows, running in a VM, and different app, different other data. But you see the model looks basically the same. Okay, that's interesting. What about on the web? Yeah, we can do that too. So here, let's make that full screen and reload. Fingers crossed here. Yeah, cool. Okay, there's that same thing backed by WebGPU on the web. Now, where this gets interesting is using this whole renderlet system that I'm building. Here's the source code effectively to generate that data. And so for the sake of time, I'm going to say, I want to do something different. And I want to take this YAML. I want to do some things like, all right, I don't like the colors. I want to change some expression. I want to be clear, this is not just attributes. This is like interesting, right? Like before, like I had a static awning height. Like, okay, like maybe we even want to make this even bigger. Like, cool, we want to make this awning at the top of the building like even larger. So this is going to basically build an entire geometry pipeline that spits this out. And this should have finished already. Sorry, conference Wi-Fi. And there we go. It looks different because I've changed different code. And yeah, now see like, wow, that building's got a huge thing on top of it, right? Cool. But where this gets even more interesting, let's go back over this Windows app. And let's see if I can actually, yeah, there we go. Whoa, that is that new building in that Windows app. And see, I didn't change any code. I didn't recompile anything. It was just a WebAssembly module that's being streamed from the internet that effectively is generating this data in real time. So, yeah, it worked. Awesome. Okay, so takes us to the end. Cool. And yeah, so links to more info, including the YAML I use and some stuff about Wander there, if you want to scan the QR code. This is still super early, right? So this is an open source project. You know, PR is welcome and wanted. We need to support more platforms. We need to do more, because right now, the API footprint is very focused on geometry, but we want to be able to do, well, even 3D geometry. We want to be able to do 2D, like if you want to do lines, gradients, etc. We want to be able to do dynamic shader compilation. We want to be able to put together everything that's part of the entire graphics pipeline to make it portable. I'm building a company called Renderlet, so if you want to talk more about hosting portable graphics, please come find me. And I think that's it. Questions?
Thank you.
Yes.
So, hi.
Hi.
You mentioned the WASI WebGPU piece. Can you talk a bit more about what the plan is over the next, like for the V2 API and what you're actually building as opposed to what's in that level 1, level 2 WebGPU proposal thing that's going through WASI at the moment?
Yes, that's a very good question. So like what is the difference between this and what is being built with WASI WebGPU? I think ultimately WASI WebGPU functions will be exposed like as WebGPU API code into the WebAssembly guest. So if you want to write code or you have existing code that is written against the WebGPU API, that will work out of the box. And that will work in Wonder, or that will work in any other host as well. I think the direction to go with something like Wonder is building a higher level rendering framework. So you don't necessarily have to write all of that raw web GPU code. You can write, you can write a more higher level. You can write a higher level API and a higher level abstraction that then ultimately can generate code that is then run against the WASI web GPU API. So like a good example of this would be SVG, like Canvas APIs, for example, right? Like you as an application developer shouldn't have to write all of the code to take a vector and rasterize that yourself. There is a platform layer to do that. And likewise, I view Wonder as like that higher level API that wraps the underlying GPU APIs like WebGL in that case, WebGPU in the new case. So I don't know, does that answer the question? Yeah. Yes, right there.
So basically, if in your case, where is all of the platform based specifically? So basically, I want to run on Vulkan, for example. Where is defined and where is compiled? Where is physically all the shaders and all of the platform GPU specific code is compiled inside the WASM or inside of the host platform? Different
answer for V1 and V2. So for V1, it is in the host platform. And so the host SDK, which is open source, so like I don't support Vulkan. If you'd like to contribute Vulkan support, I'd appreciate it. Basically, that is the drive. Like you will have the drivers for the different platforms there. So that's where we take data in a specific format out of WASM linear memory, copy it, and build GPU buffers, textures, etc. off of that. For shader code, we don't do that yet, but given the direction this is going right now, the shader code would be exposed through WebGPU in V2 to the guest. So with that, the WASM guest could programmatically generate shader code that then goes over shader compilation APIs, which are exposed by WebGPU from the host into the WASM guest. If it has, if you have a shader you already want to use, you can embed that in the WASM payload just as data, right? If you have shaders you already use on the host side, like let's say you're using this like a plugin system, like you're a CAD application, and all your data looks the same, and you want to give people an API that like lets them embed third-party objects in it, but you still want to shade it the same way, you can still use the host side shader too. That's fine. So I don't know, sorry, kind of nuanced answer, but right now the shader, like the platform-specific code is in the host. With V2, through WASI WebGPU, all of that will be exposed to the guest if that's what the guest wants to do.
Oh, okay, got it.
Any more questions? Awesome, thank you.